Welcome to Module 6, which is looking at thematic classification. So thematic classification is now moving into the post-processing steps that we do in digital image processing. So remember, it goes from pre-processing to processing and analysis. Then we go into post-processing, and then there's presentation. So thematic classification falls under the post-processing step. This is the whole idea of this one is to take our image with the values that we have and categorize it in a way that we can make decisions, we can generalize, we can talk about it, discuss it, and make those relationships, those spatial relationships that we can make on a map. A lot of thematic classification that comes out of remote sensing ends up in a GIS system. So we're creating it for that that first part. So I'm going to start with the most complicated type of classification, and that is the supervised classification. So there's two of them. There's supervised and there's unsupervised. And they are exactly what they sound like. It just depends on what the computer is doing. So classification itself, we can group data for easier interpretation. That's the whole idea behind classification. And what we're looking at to do in classification in remote sensing is we look at everything that we have in our toolbox to create our classes. So generally speaking, your transformations that you just completed have already looked at everything. So now you can use those particular transformations to create the classifications that we're working on. So just kind of jumping a little bit around here. So once we've created our classes and they have names to them, or we go to create names for them, we have to look at something called Anderson's land cover classification, and there is a web page that is in your handout and that I've also listed on the checklist that you can go to, and you can look at the land classification there. Now in the document I give you, it only gives you 2 levels because I don't want you going into the 3rd level of classification. But the first 2 levels is like a very broad class, and then you have like land cover specifics. Because all we really can do in remote sensing is identify types of land cover with our classification in terms of like thematic stuff, we can do math and calculate it and be like, okay, leaf area index. Well, if the leaf area index is really small and we're in a forest, we're probably looking at some sort of coniferous tree. Does that fall under something that Anderson land cover classification states? So yes, we can. Same with crops. You know, what kind of agricultural area is it? And then there's different ways to identify that. So with these 3 classifications, so you're going to find a very broad class, you're going to find a very, like a little bit more specific class. And then there's also like the 3rd level, which gets more into like the material analysis. But we don't tend to use that classification very often, so that's why I don't give you access to it. So we're going to use the 2nd level, the middle level, for classification. So when you guys are creating your classifications, please make sure that you only use the 2nd classification. I do not want to see water. I want to see what kind of water. If they don't have the exact one that you know what it is or that you think that it is, that name, then just use one that's close enough, okay? And I'm okay with that. I'm not going to be there checking your classes to make sure you've named them correctly. What I'm going to be looking at is, did you use Anderson's land cover classification? There's only so much I know about this world, and it's a very narrow focus, so what you know or you can figure out, I'm happy that you've been able to figure it out. I'm not marking whether it is correct or incorrect. Then you have to validate. So once you've got your classes, then you get to go out to the field. You can also use other information. So Google Earth is a great access. So if you have your coordinates of the class that you're looking at and you really have no idea what it is, go to Google Earth, see what you can see. What is it? And then you can name it from there. So that's really the background of classification and how it works and the process we go through. But then we can get into supervised classification. So what supervised is, this is the first kind of algorithm that we can use. And it is a monitored type of classification. So as the user, you have full control over what is going on. You get to tell, say, these pixels belong to this class, and this is the process that I want you to use to be able to identify all my classes. And then this is what the process I want you to, any pixels that you don't have classified at this time, how do I want the computer to handle them? So it is a lot more user intensive. You go through, you sample your image using polygons, so you're drawing a bunch of polygons. Those polygons are known as regions of interest. They're also known as training areas. And so the the standard is that you're going to have 10 polygons per class. So lots of times you have to be dealing with a pretty big image, and you're going to be zooming in a fair amount to see these classes. You also want to have like a minimum of 10 pixels per class or something per polygon. So I would say if you can get more, that's great. You don't want to zoom in so much that you're only getting 1 pixel, because then it's not really a true sample. It's only 1 pixel. So you want to have 10 polygons for every, which those polygons are known as training areas, for every single class that you are creating. So if you have 10 classes, that means 100 polygons. These do not need to be perfect. You can draw a triangle, you can draw a square, you can draw some sort of like abstract feature. Doesn't matter what the shape of that polygon is, as long as it's only keeping the pixels that are alike within that area. So then you choose, after that, after you've done all this, while you're creating these, you are also naming your land features. And then you have your classification method, so you're going to apply the sample to the rest of the method. And this is the way it's going to do it. So there's 3 algorithms I'm going to talk about here. Only one of them really works well in NV, but depending on your band, like your transformations, some of the other ones work just as well. You might want to play around with it a little bit to get an idea of which one's the better one, but I'm going to introduce the 3 of them just so that you know what they are if you're told to do them or to choose the best one. So the first type of algorithm for supervised classification is parallel piped. We're looking at ranges. So here on my little diagram, let's say I have my first class, and my first class goes from 0 to 15. That's the range of it. So any pixel that falls within this range is going to be in class 1. In class 2, I have from 15 to, let's say, 125. Actually, no, 15 to 100. So they go from 15 to 100 is class 2. Class 3 is 125 to 175. And then, is 125 to 200, I apologize. Then the 175 to 250. So we're going to have a bit of an overlap here, and we're going to have a gap right here. So that's how that's identified there. So what it does is we take our pixels that we don't know every single pixel that's not part of a training area, and we're only taking these ranges. So let's say this one is 10, this pixel, this dot here. So if this dot is 10, then we know that it falls between 0 and 15. So we know that it's going to be a part of class 1. For class 2, we have between 15 and 100, but there's the pixel we're looking at doesn't fall under that. What happens if it falls at like 112? Well, it doesn't actually fall into a class at that point, so therefore it becomes unclassified. Then we have the other issue of what if it's 190? Well, 3 goes all the way to 200, and 4 starts at 175. So now the computer does not know, is it part of 4 or is it part of 3? So now it just says, you know what, I'm just going to unclassify it. This is really important when you are creating your training areas, especially with this. So for those of you who like to try to keep things as simple as possible, and you're like, I'm going to put in as little amount of work as possible, and you just draw big blobs everywhere, and you're going to classify it, well, your entire image is going to have ranges that overlap, and it's going to come back black. So I can tell you by looking at your result what your training areas look like just because of that. Because all it takes is this 1 pixel that is out, or this one here that is out, that's not there. and it's like this one pixel that should have been in 4, but you accidentally put it in training area 3. Now this whole area in here from those two overlapping, all those pixels become black. So this is very sensitive to what you do with your training areas. Advantages of doing this is that it's extremely fast. It gives you a really quick overview of what you need, and it does have a place for unwanted data to go. So let's say that you're looking at your forest and you need to know like 3 different classes of trees. So you create these 3 classes, but then there's a river that's running beside it. Do I really care what the river is? Actually, I don't. So it can be unclassified. Do I care about the meadow beside it? I don't. So because it's not part of the trees, so then I can get rid of that. So the nice thing is I can just say anything that it doesn't matter can go into unclassified. So it does help that way. And the problem with this type thing of algorithm is the unclassified class in confusion. So these overlaps and gaps do end up, you don't know if the point is in this region or if it is in this region, right? You don't know if it doesn't fall into that or if it's in some sort of weird overlap. And so you can't identify between those two. It just all goes into one big class. So it also is very sensitive to noise. I'm saying noise, but really it means error. So if you don't create those training areas very well, then it's going to be very sensitive and give you a lot of errors with that. So that's parallel piped. The next one is minimum distance. So this time round, I take my average of each training area and I plot it onto my spectrum. So I place it, and then what I say is any new pixel that I am trying to figure out is going to go to the closest average. So here, let's say my average is 10 in class 1, and my pixel is 8. It's going to fall in class 1. So here's class 2, which is 50, and then class 3, which is at 150. Those are the averages. And let's say it's 115. It's going to say, oh, you're closer to class 3, so therefore you fall in class 3. And the same with like 190 to class 4, which is at 215. Between this one and this one is actually closer to the 215, so it's going to say it's part of class 4. So this one is also very simple, so it's very fast. It does fill in the entire image, so you have everything is classified. Every pixel belongs to a classification. So it's much less sensitive to any kind of noise, which is kind of nice. So visually it works really well. But the disadvantage is that everything gets classified. So if you missed one type of class in your image, suddenly it's getting classed as something else. And that makes things really, really confusing again, because you can't separate them. So you don't really know. It also doesn't even consider variance. So, sometimes one class might actually have a large range. Like forests themselves have a huge range of like what to expect for electromagnetic spectrum numbers and intensity numbers, and it's a really big spectrum. So if it's like, okay, well, class 3 is a very big class, and let's say class 2 is a really small class because it's only looking at perhaps a type of bush, one particular kind of bush. So now if something, let's say that the range 2, like for class 2, maybe really the top number might be 75. If for number 3, if its bottom value is 80, number 75 is going to go to 2, but maybe it's actually part of 3. So like the overlap of the range and such, it's not because it's going to the nearest one. So sorry, I did that wrong. So let's say this is the top value of this is 80. No, 75. So the top value of this is 75. Let's say the bottom value of 3 is 75. But I say that the unknown point is 80. It's still going to end up in class 2, even though it didn't look at that variance of what number 3 does. So that's what it means by not considering variance. So the spread of that particular class and the variation within that class, it doesn't take that into account. So with supervised classification, the third algorithm is maximum likelihood. So maximum likelihood is based on probability. So now we're actually accounting for variance, which is kind of nice. So it goes by what class is it most likely to be a part of. So we can see how we have like bell curves here, and those bell curves represent every class as we go. For example, here I might have a gap, and that's okay. We did in maximum likelihood, it's okay to have that. This is significantly more accurate when it works well. NV sometimes has issues running it. You have to be very cautious about how you're running it and what your training your training data looks like. So because if they're not quite accurate, then you're going to end up with issues in here. So and then but the unclassified class is a nice thing because you can leave out information that you don't want involved. Then some disadvantages is that it's slow and complex because you have to do the probability calculation for every single pixel. And then it also uses more computational memory as well, so you have to have a little bit more powerful computer. And I guess another disadvantage is that it doesn't necessarily always work. So, but then once you're done that, then once you've run this algorithm, then it's done and it's all ready to go. So that's supervised classification.